Hello, this is a review of the essay on the nondeterministic fuzzy automata by Yuan and Yeshinori Zavak. To tell about the nondeterministic fuzzy automata, the first thing we should denote is fuzziness. Let's tell about fuzzy sets. Fuzzy set is a set of tuples x and mu, where x is an element of some universum, and mu is a real number from 0 to 1. Mu is called the membership function, and mu of x means degree of membership, how much this x from universum presented in A. Fuzzy sets has same classical operations like usual sets, but here they are a little different. For example, inclusion in fuzzy set is denoted the way that each x from universum, for each x in universum, membership of this x in A is less or equal than membership of this x for B. Equivalence is the same as inclusion, but here is strictly equivalence, standard complement, which means all except A is, as you can guess, x, and probability 1 minus membership x. Intersection. For each x we choose the minimum of memberships of this x in A and B. And for union we choose maximum. There are some extra characteristics of the fuzzy sets which can be denoted for classical sets. Let's look at them. The first one is a subpart of fuzzy set A. Subpart is a set of all elements of universum which are presented in A. That means that it's all elements of universum where the membership of this element is more than 0. Kernel of fuzzy set A is a set of all elements of universum where membership function is strictly equal to 1. Height of this fuzzy set is least membership for any element in this fuzzy set. This is just a number, and we can make a scale product of a real number lambda which is from 0 to 1, and fuzzy set A. Scale product of lambda and A is a set of tuples. Our first element of each tuple is x from the universum, and the second is a minimum from membership function of this element in a set and lambda. So scale product borders the fuzzy set from the side. So if we can take a fuzzy set, show as a graph, with different memberships, and we choose lambda like this. If our first set had this graph, our new set will have this one. We'll speak about three types of fuzzy automata: deterministic fuzzy automata, non-deterministic fuzzy automata, and non-deterministic fuzzy automata with epsilon moves. The simplest case is a deterministic fuzzy automata. Deterministic fuzzy automata is a tuple of Q, which is a finite non-empty set of states. Sigma is a finite input alphabet. Delta is a function which maps production of Q by epsilon to a set of all fuzzy subsets on X, where X is a universal. In our case, it's Q. Q0 is the first initial state, and F is a set of final states for this set, of course, too. Set of final states is in a set of all fuzzy subsets of states. The main difference from a usual finite state automata is a transition function, which maps product of set of states and element of input alphabet to some possibility distribution on this set of states. And the fuzzy set of final states where for each state this denotes the possibility degree to which Q is into the final state. Another big difference between finite and fuzzy state automata is that fuzzy state automata can be in a few states simultaneously. For example, if we had Q zeros and input symbol A, it can with some possibility go to state Q1 and with some possibility in state Q2. So actually we can denote transition function like this, which means that with some possibility automata in state Q with input A may enter state P. So so if we want to denote this as a transition function that from state Q by input A, our automata can, with some possibility, reach the state P. We can denote extended transition function on a product of a set of states and clean closure of input alphabet. To do it, let's watch on two cases. The first case is on the empty string. This is just a single term for the function, which means that for this Q, membership function is equal to 1, and for all the other Q's states membership function is equal to 0. The other case is when we speak about input string. Let's look at string as a concatenation of some string and some symbol which is at the end of this string. The result is union for all reachable states. The transition function from initial state by string to this state concatenated with a transition function by one element. Let's now extend our automatas and look at the non-deterministic fuzzy automata, which is the same tuple as we've seen before. But we have here some different transition function which now maps this product to a subset of possible transition functions of possibility distribution. What this means, if we have deterministic fuzzy automata on each input, we had only one transition function which with different possibilities lead us to different states. In non-deterministic fuzzy automata, we can have more different transition functions on the same input. So deterministic fuzzy automata doesn't allow non-deterministic choices between transitions involving the same input symbols. In non-deterministic automata, same input symbols can result different transition functions. Our last automata is a non-deterministic automata with epsilon moves or spontaneous moves. It's the same tuple as we have seen before. But now our transition function is not only for input alphabet, but it also accepts empty strings or spontaneous moves. So for any state we can denote big delta or closure of Q, epsilon closure. Which is a set of all states reachable from this one by a sequence of spontaneous moves. And in a non-deterministic automata with epsilon moves, we can by this denote extended transition function.
Transition by spontaneous move from state Q is equal to epsilon closure by Q. And transition by word SA, where S is a word in sigma big and A is a single symbol from the sigma, it is equal to a union of epsilon closures of memberships of S by P multiplied by membership of P. Such that membership of S is an extended transition from Q by S. P is in a set of states, and membership the membership of P is a transition from P by A. Thank you for your attention. Thank you for your attention.